Good morning. My name is John Hang, and today I will present my cloud security assignment 2. This assignment covers 4 main areas: SAR3 for data integrity, Kerberos for authentications, Diffie-Hellman and IKV2 for secure key establishment, and SSL-TOS for secure web communications. My focus is not only on calculations, but also why each security mechanism is needed. This slide give an overview of 4 questions. Question 1, use SAR3 in the context of Amazon S3 to protect data integrity. Question 2, combines AES with the Kerberos to provide authentications and freshness. Question 3, use Diffie-Hellman for AWS side-to-side VPN, and then use the IKV2 to authenticate the key exchange. Finally, question 4, analyze SSL-TOS with an ephemeral key. The main idea across the assignment is that cryptography is only secure when the protocol also protects identity, freshness, integrity, and key material. For question 1, I first prepare the inputs of SAR3 256. The assignment requires exactly 200 bits of my personal information, which is equal to 25 bytes. My selected input and its hexadecimal are shown here. SAR3 used a small construction with a total Keccak state of 1,600 bits. But for SAR3 256, the rate is 1,088 bits, and the capacity is 5,012 bits. The rate is the part that directly absorbs the message, while the capacity stays hidden. This hidden capacity is important because it provides the internal security margin for the small construction. I also applied the required SAR3 padding before starting the first permutation round. Keccak round contains 5 transformations: theta, rho, pi, chi, and iota. Theta begins diffusion by storing each length with correction values derived from neighboring column parities. Rho and pi represent redistribution. Rho rotates bits within each length, while pi relocates complete length across different Keccak state coordinates. Chi introduces the round main nonlinearity by combining neighboring lengths through NOT and SOR operation. Iota adds a round-dependent constant to length 0, 0, breaking symmetry between otherwise structurally identical Keccak rounds. Here, I show one representative length from my actual calculation instead of reading all 25 lengths. The initial values of length 0, 0 change after theta, then pass through rho and pi, change again after chi, and finally becomes the value shown after iota. My complete 5x5 state matrix is shown at the bottom. So as you can see here, this the first, and it's matched the first length. This confirms that I successfully calculate all 5 transformations required for the first SAR3 round. The important point is not only the final value, but how each stage progressively change the internal state. Move to question 2. In this question, I implemented AES-CBC because Simplified Kerberos relies on symmetric encryption to protect tickets, authenticators, and authentication server responses. How can I do this? CBC changes plaintext blocks by storing each block with the previous ciphertext before AES encryption using this formula. And for decryption, the reverse process uses the previous ciphertext block again. I validate my implementation against the official NIST vector before trusting any Kerberos output generated from the cipher, because matching the reference ciphertext demonstrates that both AES encryption and CBC training were implemented consistently for the required tests. So as you can see here, the ciphertext and the expected ciphers is the same, so it's matched together. In phase 1, it lets the trusted authentication server distribute one temporary session key through 2 independently protected communication paths. With the client path, the client receives session information protected with KC, while the server receives equivalent credential inside the server ticket. The client can transport the ticket without rewriting it because only the server possesses the long-term key KS. My section key, nonce, lifetime, and final 64 bytes tickets are shown at the bottom. One important limitation is that this assignment uses Simplified Kerberos. It doesn't separately implement a TGT and the TGS stage, so my ticket is a server ticket, not the ticket granting ticket. In phase 2, the ticket and the authenticator works together. The ticket proves trusted credential distribution, while the authenticator proves current session key for sessions and freshness through a timestamp. The server accepts John only after ticket decryption, identity matching, timestamp validation, and confirmation of 8-hour lifetime. Why it is important because a capture ticket alone is insufficient, because replying it without a fresh authenticator should fail the server's freshness checks. So what's the mutual authentication? So the mutual authentication completes when the server returns the timestamps +1 encrypted under the established client-server session key. So in my implementation, the timestamp is 1/16, and the server processes it with 2 seconds later. The server then returns the timestamp +1, which gives 1/1601. When the client verifies this result, the mutual authentication is successful. Question 3 focuses on Diffie-Hellman key establishment for AWS side-to-side VPN. First, I generated two 160-bit random value, then derive the private exponent for John and Hoang using SHA-1 as required by the assignment. Each side generated a public value using the modular exponentiations and exchanged only that public value. John then used Hoang public values with his private exponent, and Hoang performs the corresponding calculations. So it's the share key here. As shown in my result, both calculations produce the same result. So John series and Hoang series is true. My program also perform independent verifications, and both check returns true. For the security purpose, the secret itself never across the network, which is the fundamental confidentiality benefit for the Diffie-Hellman key establishment. However, basic Diffie-Hellman has an important weakness. It establishes a correct share secret, but provides no proof about who generated each public value. So the attacker intercepts both public values, substitute attacker control values, and establish separate secrets with John and Hoang. In my attack, John first sends YA, but the attacker intercepts it. The attacker replaced this with YM1 before sending it to Hoang. The same thing happens in the opposite direction with Hoang's public value. As a result, John and Hoang do not share one secret with each other. Instead, the attacker knows both secrets. The root cause here is that the vulnerability is missing peer authentication, not broken modular arithmetic, quick exponentiations, and failure of Diffie-Hellman mathematics. Now, IKV2 solves this authentication problem in two main stages. IKE SHA-init exchange algorithms, Diffie-Hellman values, and freshness. The IKE-auth then carries identity, certificate, and authentication data that binds each peer to the preceding Diffie-Hellman exchange. With X.509 and AUTH, the X.509 certificates associate identities with just this public key, while AUTH prove possessions of corresponding private authentication key. So how can the IKV2 makes the man-in-the-middle fails? That the attacker may substitute Diffie-Hellman values, but cannot authenticate those substitutions at John or Hoang without legitimate private key. Question 4. Move to SSL TOS handshake. The assignment requires the ephemeral public exponent to be the largest prime factors of my student ID. After factorizations, the largest factor is 1021, so that the ephemeral exponent is 1021 or 03 FD in hexadecimal. The temporary RSA's modulus and my server key exchange signatures are shown here. But the most important question is that why must the server sign the ephemeral key? This signature prevents the silent ephemeral key substitutions by cryptographically binding the temporary key to the authenticated website identity. Without a signature, an attacker could replace the temporary key and make the client encrypt to the attacker. But with the signature therefore binds the temporary key to the authenticated certificate identity. After authenticating the ephemeral key, the client computes the pre-master secret. So the pre-master secret is the SHA-384 of my student ID, so I can get this result. Because the 384 bits secret is smaller than the 1024 bits ephemeral modulus, so it fits the simplified RSA calculation. The client then encrypts the PMS using the authenticated ephemeral public key. The resulting client exchange starts with 24A4 and is shown here. I also performed inverse RSA calculations on the server side. The recover value exactly match the original PMS. This confirms that the same temporary key pair was used consistently. This slide separates three different security questions: server authentication, client authentications, and forward security. First, the server is authenticated. The client validates The certificate obtains the certified RSA public key and verifies the server key exchange signature. This creates the just chain shown here. However, the client identity authentication is not provided. Because the client identity authentication is absent, because this handshake includes neither a client certificate nor a certificate verified proof. Forward security is also needs an important qualification. Ephemeral RSA improves forward security only if every temporary private key is unique, protected, and securely destroyed after use. The very important limitation is here that the assignment SHA-384 of email secret is deterministic, so the construction should not be equated with production grade DHE or ECDHE PFS. So I would not call this production grade perfect performance security. Static RSAs provide no forward security. The assignment gives only the conditional forward security property, and modern DHE provides production grade PFS. To conclude, each question demonstrates a different security lesson. SHA-3 shows how diffusion, nonlinearity, and sponge capacity support data integrity. Kerberos shows that the authentications also needs trusted credential distribution, freshness, and replay protection. Diffie-Hellman shows automatically secure share secret is still vulnerable when the participants are not authenticated. Finally, SSL-TOS shows the importance of separating long-term identity keys from temporary sessions key establishment. Overall, the secure cloud system requires correct cryptographic calculations and correct protocols design working together against the realistic security threats. Thank you very much for listening. That concludes my presentation, and I'm happy to answer any questions or explain any parts of my implementations for more details.